All right. So we'll talk about some of the definitions first. What is a sequence? How is it defined? What does it look like? And then we'll look at practicing a little bit with some sequences, finding terms. And then finally, we're going to look at how do we write a sequence, write the generator for a sequence, if I give you some of the terms in a sequence. So there's two types of sequences. All right, so the first type is what we call an infinite sequence. So let's define what an infinite sequence is. So this is a function. All of our sequences will be functions, by the way, whose domain, so inputs, is the set of positive integers. What does that mean? That just means numbers like 1, 2, 3, 4, 5, and so on. So our inputs have to be positive integers. So we won't have any negative inputs. We won't have any fractions. We won't have any decimals. The inputs have to be integers. So only your counting numbers. We could use 0, and we'll talk about that in a minute. It's just not done every time. So the outputs are written like this. So a sub 1, that's how we say that. I'm just going to put a few in here. So anytime in mathematics you see ... that just means that whatever you're looking at continues with whatever pattern you're seeing. So what I'm saying here is that my outputs are written as a sub 1, a sub 2, a sub 3, and so on, up till some random term in the sequence, which we'll use to help us write our generator, and then it continues on. That's what an infinite sequence is. It does not end. It keeps going. These are just the ways we represent those terms without knowing what they are. So when I actually write out the sequence, you'll see numbers written there, like 1, 3, 5, 7, 9. Like that's a sequence. It's a sequence of odd numbers, okay? This is just our notation for how we would represent any one term in that sequence. All right, now the big difference is then we could have a finite sequence. Okay, so an infinite sequence goes on forever. A finite sequence does not. It has a place that it stops. So a finite sequence is a function whose domain is, we'll say, the first n positive integers the outputs look like, so this time I'll go a sub 1, a sub 2, a sub 3, a sub 4, ... a sub n. And it stops at a sub n. So it doesn't keep going like it does for an infinite sequence. With the infinite ... we can see we have that ... after the nth term. Finite, it's the nth term is the last term. So we don't go any further than that term. So nothing too crazy there as far as like the difference between the two. The big thing I want you to understand is that we're writing this in a mathematical way so we can understand how to represent these things in more of a generic way. So just as a little note here, most times the sequence will start with the first term. We'll say with n equals 1. Sometimes we'll use n equals 0. And that seems like kind of a weird thing to say. But I might say, hey, for this sequence, I want us to start out with our beginning term as the 0 term. That would just mean plug in 0 for n. But most of the time, we're going to see that first term as being n equals 1. We'll just say term 1, term 2, term 3, and so on. Okay, so let's just kind of play around with the idea of a sequence here. And let's work through our first example as just writing the terms of a sequence. In other words, I give you the sequence generator, the thing that's creating the terms in the sequence, and we just find some terms. So we'll do a couple of these just to get in the practice of doing this. Our first one, our generator, I call it a generator. I picked up that term from our Algebra 2 curriculum, Algebra 1 curriculum. I like the idea of a generator because that's what's creating the terms in the sequence. So our generator is given by a sub n. The nth term is defined by taking 3 times n and subtracting 2. So 3n minus 2. Okay, so our generator is that. I want us to find the first 4 terms. So a sub 1, a sub 2, 3, and 4. Let's find our first 4 terms. All right, all that means is that whatever our n value is, whatever term we're finding, so in this case, we're finding the first term, that defines the number I plug in for n. So we're finding the first term, I plug in 1 for n. So I would get 3 times 1, that's my term number, minus 2. So I'm using my generator and plugging in the term number and evaluating. So 3 times 1 minus 2, pretty easy. That's just 1. So our first term of the sequence is 1. The second term of the sequence is what we get when we plug in 2 for n. So 3 times 2 minus 2. 6 minus 2, that's 4. And we could continue this process. So 3 times the third term now, we're plugging in 3 for n. So 3 times 3 minus 2. 9 minus 2 is 7. And then finally 3 times, so we'll do the fourth term, minus 2. So 3 times 12 minus 2 is 10. So our first 4 terms of our sequence, if we were going to write this as a sequence, what I would do is I would take those outputs and I would write them like this: 1, 4, 7, and 10. Now just stand back for a second, and I want to analyze this just a little bit because it'll help with what we'll do later. What do you notice about the sequence that we just wrote, 1, 4, 7, and 10? What's happening from one term to the next? You're adding 3, right? So just as a little, like, hey, notice this type of thing. We are adding 3. And then I'm even going to write our generator had 3 times n. Maybe that's a little bit of a clue. It's a little bit of like foreshadowing here. Okay, our generator had a 3 times n in it. And what ends up happening is our sequence adds 3 each time. Okay, so that's kind of, eventually today we're going to be headed in that direction. Okay, let's do one more just where we generate some terms. Make it a little more interesting. So this will be B, I guess, under this set. Okay, so my generator this time is a sub n equals 3 plus negative 1 raised to the nth power. Let me just separate these a little bit so we know they're not together. Okay, 3 plus negative 1 raised to the nth power. And all I want to do again is generate the first 4 terms. So we want to find a sub 1, a sub 2, 3, and 4. So this one does something interesting. It's using -1 and raising it to a power. And I want you to think about that. What is 1 raised to any power? If I said 1 to the millionth power, what is that? It's just 1 times itself a bunch of times, right? So it's just 1. If I said -1 raised to any power, I'm either going to get 1 or I'm going to get -1. Those are my only 2 options. So let's play around with this a little bit. So I'm going to generate my terms here. So to find the first term, I'm going to do 3 plus -1 raised to the first power because that's my n value. What is -1 raised to the first power? -1, right. So we're really saying do 3 minus 1 here. And that ends up being 2. Okay, let's try the next one here. 3 plus -1. Now we're finding term 2, so I'm raising it to the second power. What is -1 squared?
1.
Positive 1, right. So this is now 3 plus 1. Okay. Maybe you're seeing a pattern here, but let's do a couple more just to make sure that pattern is accurate. So 3 plus -1 raised to the third power. What is -1 raised to the third power? -1, yes. And I'm going to kind of talk about that a little bit more in just a second. And then finally we have 3 plus -1 raised to the fourth power. What's -1 raised to the fourth power? 1, good. So we're going to talk about 2 things in this. First of all, our sequence kind of looks a little strange, right? It's just alternating between 2 numbers. Do you think there's a way that in this sequence with that generator, that I could get any number other than 2 or 4? No, because my only possibilities with -1 raised to a power, I'm either going to get 1 or -1. So that's a little bit of an interesting piece of information. That can be really powerful. So I want to kind of talk about that piece for a second. So that -1 to the nth power. All right, so let's come over here. -1 to the nth power. And I apologize, you can put this wherever you want in your notes. I'm going to put it right here. All right, so -1 to the nth power. If n is even, what is -1 to the nth power going to be? So if n is like 2, 4, 6, 8, 10, what's it going to be? -1 squared, -1 to the fourth power, -1 to the sixth power. It's always going to be +1, yes. If n is even, we're always going to get +1. But if n is odd, then -1 to the nth power is going to be what? So -1 to the first power, -1 to the third power, to the fifth power, what's that going to always be? -1, yes. What this allows us to do is to alternate what we added by changing the sign, and just changing the sign. Now we could use that to alternate and multiply by the result. So I could say, hey, if n is even, I want you to multiply by a +1. But if n is odd, I want you to multiply by -1. So I could change that number, and it can really affect my outputs of my sequence in an interesting way. Okay, so let's talk about how we can write a generator. So not given the generator, but given some terms in the sequence. Let's see if we can write a generator. So this is our second example. This is example 2. So the first example, we talked just about how do we use the generator to get terms in the sequence. So now we are going to write the generator for a given sequence. So for example, maybe I give you the sequence 1, 3, 5, 7, ... And I want to come up with the generator for this. Now I'm going to organize my thinking a little bit here because I think it helps when you start testing to see if you've come up with the correct generator. So these are my outputs, right? These are the outputs of the sequence. So if I think of that like this as a table, A sub n are my outputs. So I have 1, 3, 5, 7. Those are what I get when I plug in a number for n. Now, n, we said, was the positive integers. Unless you're told otherwise, start with n equals 1. Okay, if I specify to start with n equals 0, that's different. But I want to start with n equals 1 unless otherwise instructed. So if I think of this in a table form, there are so many ways I could write the equation of this. But my goal is to come up with the equation. So we have kind of like some terms in between, and then we have our nth term. And I want to know what is the generator for that nth term. That's my goal. Figure out the generator. All right, so I usually start with thinking about, is there something that I'm adding to get to each term? Because that's a really easy sequence to write in most cases. All right, so think about from 1 to 3, what did we add? If we think of it in terms of adding, 2. And then from 3 to 5, we also added 2. And from 5 to 7, we also added 2. That's really nice. That's just like what we talked about in that first example. When you're adding 2, so when you're adding or subtracting, the same number each time, that's going to allow you to write a linear, it's a linear sequence. We will write a linear generator. So back in Algebra 1, you talked about ways to write the equations of lines, and that's what that's going to be. If you're adding the same number each time, it's going to be the equation of a line. There are lots of ways to do this, but here's what I know for sure. Since we're adding 2, then 2n is part of our generator. I'm writing a lot of words down, mostly because, this seems really easy when we're in the moment, but then you go to try to do this on your own and you get stuck. Like, this process can be tricky. So I'm trying to write as much down as I can just to keep us kind of with something to look back at later. All right, so 2n has to be part of my generator. So here's what I know. I know my generator has to be something like a sub n equals 2n plus and then something. Plus or minus. It could be minus, but plus something. So how on earth am I going to figure out what that something is? I've got to use the data I have. Okay, so I know that if I plug in 1, I should get 1. If I plug in 2, I should get 3. If I plug in 3, I should get 5. So when I look at this, I'm doubling whatever I'm plugging in. I'm multiplying that thing by 2. I've got to either add or subtract something to get me to this output. So I'll pick 3, for example. If I plug in 3 here, I get 2 times 3, which is 6. My output needs to be 5. What should I do to 2n to give me an output of 5? Subtract 1. Yeah, very good. Okay, so let's call this, instead of adding, let's say subtracting there. Okay, so I'm going to subtract 1. So I did no algebra there. I just looked at what I knew had to be part of my sequence, which is the 2n, and used the data to figure out what the rest of that sequence should look like. Now I'm just going to double check it. So if I plug in 1, 2 times 1 is 2, minus 1 gives me an output of 1. If I plug in 2, 2 times 2 is 4, minus 1 gives me an output of 3. Okay, so it's important that you check to make sure your generator actually works. So I'll just, check. But this is our generator. A sub n equals 2n minus 1. No, algebra there, really. You could do this algebraically. There's many ways that you could do this algebraically, but that's just my approach for that particular problem. Okay, so B maybe is a little more interesting. So with B, I have 2, 5, 10, 17. And again, I want to figure out what is my generator. Okay, so A sub n is my goal. A sub n equals something. That's what I'm trying to figure out here. I do like to organize my thinking in some kind of a chart or a table. I just think it helps you sometimes see the pattern a little bit better, right? So we know that unless we're told otherwise, we're going to start with n equals 1. So when my input is 1, I get an output of 2. When my input is 2, I get the second term, which is 5. And I'm just going to continue to put this in table format. And then we know after whatever we're given, it continues on because it's infinite unless we're told otherwise. We got to figure out what the nth term gives us as far as a generator goes. Okay. So I'm again going to start out with the idea, can I look at the difference in between each of my outputs? Can I look at how much I would add or subtract to get to each output? And that's where I always start. So I'm going to come over to my table and do this. All right, so if I go from 2 to 5, what did I have to do? If I think in terms of adding and subtracting. Add 3, good. If I go from 5 to 10, what did I add? 5, and then from 10 to 17, we added 7. Well, that's not a consistent number. So what that tells me is that it's not linear. Okay, so this, right off the bat, this can't be linear. So I know it's not linear. I got to come up with something else. There's some other relationship there. So a lot of times in mathematics, there's these little tricks that you learn as you go, but I'm going to give you one that you can use now. I look at something called the second difference. Now this, what we just found, 3, 5, and 7, that's my first difference. It's the difference between the terms in my sequence. But I'm going to look at something called the second difference. I'm going to look at the difference of the difference. Okay? So what's the difference between 3 and 5? 2. We added 2. How about between 5 and 7? 2. Also 2. That second difference being the same tells me I'm dealing with a quadratic. Okay? So this second difference is the same. That means we have a quadratic. In other words, somewhere in our sequence, our generator must have n squared in it. Okay, so that's what that means. When that second difference is the same, we have a quadratic. Our generator has to have n squared in it.
What would it look like if it was cubed?
I want to hold off on that for a little bit. I'm trying to keep them. I know you want to know.
Okay.
I'm going to put a pin in that for right now. We will come back to that. And after you see how the quadratic works, you might be able to naturally move that into a cubic, but we can maybe talk about that tomorrow if I think we have some time tomorrow. All right. So our second difference is the same. We have a quadratic. It's a generator that must have an n squared. So we know at this point, here's what we know. We know our a sub n term must be n squared. It has to have an n squared in it. That much we know. Now, as far as how we figure out how to adjust that to get to our outputs, that's going to be something that you can kind of learn to do with whatever method makes you feel most comfortable. You can think about plugging in each of your inputs, right? So if I plug in, if I just make, let me just make a table for this, right? If I have n and n squared, when n is 1, I get 1. When n is 2, I get 4. When n is 3, I get 9. When n is 4, I get 16. Let me compare these outputs that I just wrote to the ones that I need to get for my actual sequence. So when n was 1, I got 1. I need it to be 2. When n was 2, I got 4. I need it to be 5. When n is 3, I got 9. We got to get 10. When n is 4, I got 16, but it should be 17. So what should I do?
Plus
Add 1. Yep. And that's our generator. So once we recognize that it's a quadratic, then we can make the adjustments. You got to recognize the overall pattern and then adjust as needed. I want to take the sequence we just did and make one little change to it. And let's see if we can figure out how to adjust for that. So we are going to do this will be the last one. So let's take that same sequence, but instead of starting with 2, I want to start with -2. And then we'll have 5, and then -10, and then 17. So that's the only thing I want to do. I just want to make a minor change there. And notice what's happening with that. The signs on the terms are alternating between positive and negative. We talked up here how to get something to have alternating signs. This guy is how we get alternating signs. Really, alternating signs, sings. I couldn't spell signs. Or possibly even alternating terms, depending on what your sequence looks like. If you're seeing alternating signs or you're seeing alternating terms, you're probably going to have to use that. So let's think about how we would use that. In our sequence that we just did, we know that 2, 5, 7, and 10, 2, 5, 10, and 17 are going to be generated by n squared plus 1. So -2, 5, -10, and 17. The base of that would have to be n squared plus 1. So here's what I know. I know it's got to have this idea of n squared plus 1 in it at some point. That's what's generating those terms. But I've got to alternate the signs on those terms. I want my first term to be odd. I want my third term to be odd. Negative. I want my first and third terms to be negative. Odd terms to be negative. That means if I do this, if I just multiply this by -1 to the nth power, remember what we talked about, -1 to the nth power, when n is odd, you get a -1. So I'm saying when n is odd, I'm going to multiply whatever my output for this was by -1. When n is even, I'm going to multiply whatever this output is by +1. Hence giving me the negative terms for my odd terms, positive terms for my even terms. Now I just want to talk a little bit more about how we could use that in another way. So just as a little note here, again, just to remind us what we did. This guy makes odd terms negative and even terms positive. But what if we needed it the other way around? So what if I needed to have my odd terms be positive and my even terms be negative? So we can make one little change to this. Okay, so one little minor change. So let's say we wanted to make odd terms positive and even terms negative. then we would use this. -1 to the n plus 1 power. And think about why that is. If n is 1, that's an odd term. Plug in 1 to that, you get 1 plus 1, which is 2. So you end up squaring it, giving you a positive output. That's a nice little tool to have when thinking about how to write sequences and giving the generator for them. So we talked really about 3 types of sequences here, right? We talked about when you're writing the equations. We talked about, where are we at here? This guy. If you're adding the same number every time, that gives you a linear sequence. And you can write your equation using a linear format. If your second difference is consistent, then you have a quadratic. And I want to go even further and say when your second difference is 2, it's a quadratic, I think is what it is. I'm going to put a little note here. Okay, it must be 2, so not just the same. And I think that's the easy way to answer your question, is that if it were 3, we'd have a cubic. If it were 4, we'd have a quadratic or a quartic and so on. But if it's 2, we have a quadratic. And then if you want to alternate signs or you want to alternate terms, then you can use this -1 raised to either the n or the n plus 1 power. Okay, you're going to have a go formative here to work on.